Go.
Hello!
Hello, Mr. Ryan. How are you today?
Good!
Okay, so can you remind me what is a binary search tree?
Okay, so on the left side,
Binary search tree.
Okay, so it's like a binary tree.
But it's what?
On the left side, it's smaller, and on the right side, it's bigger. Of the
Can I-
parent.
Could you give an example, please?
Okay. I'll do...
You don't need to draw that perfectly. Just draw roughly a binary search tree, okay? But a binary search tree is a binary tree, right? But it has to satisfy some requirements to be a binary search tree. And the nodes on the left-hand side are strictly smaller than the parent, and the nodes on the right-hand side, on the right subtree, are strictly bigger than the parent, right? Okay. And why do we need a binary search tree? So in what traversal order does the binary search tree produce a sorted order? Sorted list. Yes, that's very nice. Look, this node, even it's on the left-hand side, but it has to be strictly larger than the parent, this parent, right?
Yeah.
It can't be like 3. If this is 3, it's not but BST. Does it make sense? Even it's smaller than 8, but it has to be bigger than 5.
Wait, I mean, I'm not... Wait.
Yeah, that's right, yes. Okay, so what kind of order? What kind of order? We have in-order, pre-order, and yeah. Breakfast search is 5 to 8 level by level.
Post order.
Post order. So which order produce a sorted list? Which order do we apply? I mean, if we apply to the binary search tree, we will make a sorted list.
Left. The one with left note.
And
Right.
I know what's that called?
I think it's post.
In order, because
In
the
order.
node is in the middle. So let's in order. So it's what? Left node, right? Because look, left node is strictly smaller than the root, right? And the right node is strictly smaller than the root. So if I go with this, that's in order, yeah? In order, because this is in the middle. If it's this in order, then it produces a sorted list, right? Am I right? Does it make sense? Okay, so today we are given this binary search tree, and if I tell you, what's the successor? You know successor? So the next one, what's the successor? If it of the node, for example, if I give you the node 5 and I want you to tell me that the successor of 5 is 8, right? Which is
Why?
the smallest number. No. The successor of the 5 is 6. Sorry, 5 is 6. Because it's in order. Yeah, is what? 2, 5, 6, 8, right? Yeah? Let's sort it. So what's 5? What's after 5?
6.
6. Yeah, that's what
How about
so
what would you return is a successor of 8?
yeah, well done. That's a good question. You just return nothing, none. You can't find anyone. But let's one edge cases. Good question. So basically, you're finding the smallest number that is bigger than 5, right? The successor of 5 is that I want you to find the smallest number which is bigger than 5, right? So it's 6, not 8, right? Because 6 is smaller than 8, which is these two are bigger than 5. Do you have how do we solve this? How do we
Okay.
solve this?
You use in order.
Yeah, in order, yes.
And then you just do the next one of the thingy.
Next one thing. So yeah, we can traverse the binary search tree and then put all the nodes in a list, and then we look for the node, right? The index, using the index function, yeah? And then we return the next one, right? Does that make sense? Yeah? Okay, let's do this, okay? Let's do this.
Let's do this.
Okay, so define in order successor root, and then we have a target. This is the target column. Yeah? Okay,
Yeah.
so now look, we have a list first. Let's call it data. Okay, data equals this. Yeah, empty list. Yeah, and then we do this define. Therefore, such we define a function which take an element. Let's just traverse the binary tree. Yeah? Okay, look, if root is none, we just return. Yeah. Okay, return. Just return. Then what? We travel which node first? The left node, right?
Yeah.
Yes. So DFS root dot what? And then what? We travel the left tree, so root dot what?
We do left.
Where? Where? Now?
After.
Look, this is recursive. We are calling it. And what should we do? We add the node root dot value data dot add. Not add. Dot append, right? Append root dot value, yeah. And what should I do after next? What should I do after next? What should I do now? I travel the left tree. I added the current node, and then what should I do? What's missing here? What should I do? I visit the left tree. I put the node.
You visit the right tree.
Yeah, the way down. And
Yeah.
after that, I have this data, yeah? This data thing, yeah? Yes? Yeah, this data thingy. I think I have to put this non-local thing, remember? Non-local. Yeah, because this is not in the scope, I have to reference it here, right? And here I have say DFS root, okay? And after that, data will contain the sorted list, right?
Yeah, and then.
Then what should I do? And then look, I will have this I equals data dot, I find it, look, index, yeah? I find the index of the t, right? Yes? Then if I is smaller than length data, yeah? If there's if it's in the smallest data, I then plus minus 1, yeah? Because if it's not the second to the next, and I can return what? Return data, I will return the I plus 1, right? Yeah? Because this is the next one, yeah? What's the term complexity? What?
And something?
Yeah, so because we're traversing the binary tree, if there are n nodes, there will be n times. I have to visit the nodes, each node, and put it in the data list, yeah? What's the space complexity?
N.
Yeah, O n. Okay.
Can't be using the data thing. Yeah.
Can we do it better? I mean, if the binary search tree is highly balanced, okay, it's very balanced, still O(n), right? Because we have to visit exactly at every node in the binary search tree. We doesn't use the fact that the left nodes are smaller list than, yeah, the node, and the right nodes are bigger than that, right? We have to visit it all at once. Can we do better?
Maybe we can.
Maybe we
can't.
Okay, so this is clear, yeah, Eric? This is clear, yeah?
Yeah.
Look, if I is we find the t, the index of t. If it's next one, if I plus 1 is still length smaller than the length data, then we can return the next one, right? Otherwise, if this if condition doesn't satisfy, what does it mean? What does it mean?
It means that.
It means what? It's the which element, and we can't find the next one. Which element?
The last one.
Yeah, if it's the last one, it doesn't go in there, right? Because if the last one, data I plus 1, is out of boundary, you can't find I plus 1, right? Yes? Does it make sense? Look, this if this array is 1, 2, 3, right?
4, 6,
1,
7.
2, 3. Okay, ARR 0 is what? ARR 0 is what?
1.
Yeah, and ARR 1 is what?
2.
ARR 3 is what? I don't know. 0 ARR 2 is what?
3.
ARR 3?
4.
No, it will be, the computer will complain. Because look, AR only has 3 elements. So you're asking for the 4th. Okay? And then there will be a runtime error. So the computer will complain and will throw an exception and telling you that you can't do that. Okay? There's a problem, there's a bug. Yeah, does it make sense?
Mhm.
So that's why we have to check. If I plus 1 is smaller, is still within the boundary, then I can return the next one, right? Otherwise, it's the last element, and we can't find the successor. Okay, we can't find the smallest element that is larger than the last element, right?
Mhm.
Yeah. Okay. So another algorithm. Look. Let's do this. 2, 0, 1, 4, 3. Okay. This is the binary search tree, right? Yeah.
Why can't you do 3 then 4?
Or you can do 3 and 4. It's the same, yeah.
Mm.
The in order will be 0, 1, 2, 3, 4. Yeah. Okay.
0, 1, 2,
It's a sorted
3,
list. Yes.
4.
So look, if I just tell you, if I want to look for number 2.
It'll be number 4.
Yeah, I know. If I want to look for number 4, for example, okay, I want to find the successor. Maybe this is not a good example. Maybe 0. If I want to find a successor next to 1, a 0, there will be 1, right? Okay, so is 0 smaller than 2?
Yeah.
I go this way, huh? Yeah.
Is 0?
Is 0 smaller than 0?
No.
No, I go to the right. So what does it mean? It means that, what does it mean? Look, so we are given this t, we can traverse the tree by comparing the value to the node, yeah? When the value is smaller, when the list value is smaller than the root value, like if I want to find a 0, and then I will update the answer, the node. Because look, if this t...
So you just subtract the target from the that thingy?
Not exactly. Look, if this the successor, let's call it answer, okay? This is the answer we are looking for, right? At the beginning, it's none, right? Okay? Yeah? And this target t is equals 0, right?
Yeah.
It's the number we are trying to find. Next bigger than t, the smallest number bigger than t, which is 1, right? Okay? So if t is smaller than the root is here, right? Yeah?
Yeah.
It's smaller than 2, so I should update the answer to 2 and go to the left. Why is that? Because if this number is smaller than 2, then 2 is bigger than the 2 is bigger than the answer, right? Am I right? Yeah? Look, you need to think about this logic, okay? If this number we are looking for, t, is smaller than a 2, so 2 is bigger than a t, is bigger than t, right? Right?
Mm-hmm.
So we set this answer to 2 now, because we find a number which is bigger than t. Does it make sense?
Yeah.
So I go here. Okay. If 0 is smaller than 0, no.
No.
I go to the right, right? Then I don't get it. I don't need to do anything. But look, if 0 is smaller than 1,
Yeah.
yes, smaller than 1. So every time it's smaller, I update it to this, right? And I go to the left, which is nothing, and I end it. So look, the answer is 1. Yeah, does it make sense? Yeah. When you go to the left, what does it mean? It means that the root, the current node, is bigger than the value you are looking for. Then it's possibly the answer, right? It's possibly the answer. I have to update the answer.
What happens is the root the answer?
If it's the answer, okay. How about? Okay, so good question. How about if I put 0 and then I erase that one thing? Okay.
Yeah.
Okay. At the beginning, we are still looking for 0, which is the next one will be 2, right? Yeah.
Mm-hmm.
If 0 is smaller than 2,
Yeah.
yes, then it means 2 is bigger than 0, right?
Mm-hmm.
Yeah, and then I update the answer. This is the candidate. It doesn't mean it's the final answer, right? It just means that 2 is bigger than t, but we are not sure if it's the smallest, right?
Mm-hmm.
Okay, now I go to the left. Okay, is 0 smaller than 0?
No.
I go to the right, which ends in nothing, ends. And then the answer is 2, the last one, yeah?
Mm-hmm.
Okay, should we try another example like
What happens
3?
if there's one there?
Sorry, which one?
What happens if there's one there?
Okay, let's the example I just show you, right? Remember? Yeah. How about let's take this example 3,
3.
and then you give me the answer 4, right?
Yeah.
Let's do this number 3. At the beginning is nothing. Is 3 bigger than 2, smaller than 2?
No.
Go to the right. When you go to the right, you do nothing, right? When is 3 smaller than 4?
Yeah. Yeah.
I go to the left, but I also update the answer to 4, right? Because 4 is bigger than 3, it's possibly one answer, right? Okay, is 3 smaller than 3?
No.
I go, no, and I just go right. And end, let's end it. And the answer is 4. Does it make sense?
Yeah.
Okay. So it's a bit tricky, right? But it works, yeah? It's a bit tricky, right? So the thing is that when you turn to the right, when you compare turn to the right, it also means that the root is possibly one of the answer, right? Because it's bigger than the thing you are looking for. But we are not sure if it's the smallest, right? Then we keep visiting, we keep updating, right? When you go to the right, you do nothing. When you go to the left, you are making you are towards the answer, right? Because you are making this answer smaller, right? Yeah, right.
Yeah.
When you go to the left, it's bigger than the answer, but it's smaller. So we are getting close to the final answer in this way. Yeah. Define. Okay. Look, answer. Yeah, equals nothing. Okay, none. Yeah. You tell me. Okay. While root. Okay. While root. Yeah.
Color.
If t is smaller than root of value, what's missing? Okay, else what? And here, what should I do? If t is smaller than the root of value, what should we do? What did I just say? I need to do what?
You shall.
What?
Update the thingy.
Update the thing which is answer, yeah?
Yeah.
Answer equals what?
Equal one.
Answer, no. Answer equals which value? This value or?
Okay, the root of value thingy.
Yeah, root of value. And which direction should we go?
We shall go.
Go to the left or right? Root equal root of left, okay?
Yeah.
And then what should I do if it's bigger? If it's not smaller, what should I do? Root equals root of what?
Root of what?
Yeah, well done. And then what's missing here? Return what?
Answer.
Answer, well done. Okay, you see, this is shorter, right? Compared to the previous one, the depth of search, right? Remember, you still remember?
Yeah.
What's the term complexity? A bit tricky. What's it? Oh, what's h? Oh, h. Yeah.
Height.
Height. Yes, well done. Oh, h. Yes. And what's h equals? You can say oh and h equals what? If it's a balance.
Height.
If it's a highly balanced search tree, what's h? Oh, h is the height. You can say okay. And also, if I want to say n is the number of the nodes in the root, oh what?
N. No.
Oh what? If it's a binary search tree, n nodes and highly balanced.
O-N-H.
No.
N log n?
No. Come on.
O log n?
O log n. Come on. Log guessing. Look. Why is O log n? Look. This binary tree. Okay. Look. Alright. How many nodes are there?
7.
7 nodes. Okay. Height is what? 3. Yeah.
Yeah.
Height equals 3 and node equals 7. So it's roughly 8. Okay. So log 8
Which
is 3. Okay. Does it make sense? Yeah. Because look, 2 to the power 0, 2 to the power 1, 2 to the power 3. In the reverse, it will be log, right? That's why in the binary tree, when you are every time I go to the left or right, right? So every time I cut, I abandon another half, right? Am I right, Eric?
Yeah.
So every time I abandon half, so let's log n. Does it make sense? Or you can say OH because h is the height. Does it make sense?
Yeah.
What's the space complexity?
I
Oh what? Come on, do we use any space here?
1.
Come on, be confident. On 1, yes. We are not using any space, right?
Yeah.
We are not using any list. But previous one we have a list, right?
Yeah.
Answer list. That's why it's on 1, right?
Yeah.
Yeah, that's good.
Yeah.
Okay, wait. Wait. Okay. What's 2 here? What's 2 here?
We are the finish.
Come on. Answer thingy, yes. Answer thingy what?
On the finish equal billion. Okay.
Answer equals what? We're updating the answer. Answer equals what?
Answer
Equals what? Answer equals what? We go to the left. We update the answer to load value. Yes, come on. Write it like a man, not like a little girl. So small. The printing. Okay. And then what? We go to what? We go to the left or right?
Left.
Yeah. Because it's smaller, we go to the left. If it's bigger, we go to the right. Yeah. Does it make sense?
Left. Yeah.
Left. Come on. Lu equals lu dot left. What is it? Lu.
Left.
Well done.
Ta-da!
Okay, that's it for today.
Bye.